Continue with the acid-base net ionic equation. Anyway, so here is an example of a strong acid, weak base. And this one, it takes a little doing to write the formula for it, or the equation, because it's not like a double replacement reaction. So what we have is we have hydrochloric acid. That's a strong acid, so that's a strong acid. And ammonia is a weak base. So we'll have hydrochloric acid plus ammonia. Ammonia is NH3. And basically what happens is this can be aqueous, this can be aqueous, but what happens is the ammonia will combine with the chloride, and it's going to make ammonium chloride, NH4Cl. All right, and ammonium chloride is also a substance that is aqueous. Okay, you can double check the chart if you wanted to, but ammonium, like almost all ammoniums, are aqueous. If you look across, you can see they're almost all aqueous, and it is. Okay, and so going back to the thing here, so ammonium chloride is aqueous. Now, the thing is, what we can do is we can start by writing the things that are strong and how they will break apart into ions. So the HCl is going to make H plus, and it's going to be aqueous, plus Cl negative, it's also aqueous. Now the ammonia is a weak base, so we're not gonna, it doesn't necessarily dissociate into ions in this equation. So we're just gonna write NH3, but we'll leave it together and we'll call it aqueous. But then we have the NH4, Cl, the ammonium chloride, so the NH4, which is aqueous, okay? And then that will be positive 1, I forgot the charge, and the chloride is negative 1. Okay, then what you do is you look at it, make sure it's balanced, which it is, all right? But then you need to cancel anything that's aqueous on both sides. And you can see that the chloride is a spectator ion. Okay, it's aqueous on both sides. We can't cancel out the H plus because there's no H plus over here that's aqueous. So the net ionic equation for this is you have an H plus ion, okay, which is going to react with this ammonia molecule. And what you're going to get out of it is the ammonium ion. Now let's make sure it balances. 1 nitrogen, 1 nitrogen, 4 hydrogens, 4 hydrogens. That balances. How about the charge? 1 positive charge here, nothing here, and that's going to equal out the 1 positive over here. So the charge and atoms balance. That's what you're always looking for. Okay, so that's an example of a strong acid, weak base. All right, there's a couple other types that we can do, and so let's see here. Let's start with this iron 3 chloride with sodium metal. All right, so anyway, we'll write the equation here. This one's not an acid-base one. So we got FeCl3 plus sodium metal. Okay, so we're going to say the iron 3 chloride is aqueous. The sodium metal, of course, is a solid. Now what's going to happen is the sodium, this is a single replacement, is going to go with the chlorine and make sodium chloride, and you should know that that's aqueous, salt water, you know, the ocean. And then what's left over is the iron, and the iron would become a solid. Okay, now we need to balance this equation, so we're going to put a 3 here and a 3 over here. Now we can rewrite anything that's aqueous on both sides. We'll cancel out, but before we do that, let's write out what we got here. So the iron 3 chloride is an ionic compound, and it's aqueous, so it's going to break down into ions. So notice how I moved the 3 in front of the chloride, because it's not Cl3, it's 3 chloride ions when this dissociates in water. Plus 3 sodium, that's a solid, no charge on that. That's going to make 3 sodium ions plus 3 chloride ions, and they're going to be aqueous, plus iron, which is a solid. Now, anything that's aqueous on both sides we can cancel out, like the chloride ion. The chloride is a spectator ion. You see, we can't cancel out the sodium because it's not aqueous on both sides. Now we can rewrite. So Fe is 3 plus aqueous plus 3 sodiums solid gives 3 sodium ions plus iron solid. Now, I forgot to put aqueous here. All right, now what's tempting for a lot of people to do is say, hey, I can reduce, I don't need the 3 here and the 3 here. But if you were to cross those off, you would have a problem because your charge wouldn't balance. Okay, because this side, the net charge on this side is 3 positive. That means the charge on this side has to be 3 positive. And if you cross this 3 off or reduce the sodiums, that's not going to be true. So you got to be careful. You can't just reduce these 3's in this case. All right, let's try another one. Okay, acetic acid, which is HC2H3O2. Remember, that's a weak acid. Plus baking soda, which is sodium hydrogen carbonate. Okay, this one's aqueous, this one's a solid. What's going to happen is you get sodium acetate, NaC2H3O2. That will be aqueous, plus CO2. Now CO2 is a gas, that's G. Okay, plus water, which will be a liquid there. All right. Now if we balance it, I believe it should already be balanced, I believe. All right, which I think it is, so hopefully we're okay to go there. Now, anyway, we can look at things and say, okay, HC2, this is weak acid, we can't break it apart, so it stays together. All right. But the the sodium hydrogen carbonate, that's an ionic compound, but it's a solid. Nope, so I was going to go crazy there. Can't break it apart, it's a solid. All right. Over here, we could break this apart because it's an ionic compound and it's aqueous. Okay, but we can't break apart the CO2 because it's a gas, and we can't break apart the water because it's a liquid. That's supposed to be water there. All right. Now, nothing is aqueous on both sides of the equation that we can cancel out. So there are no spectator ions here that we can cross off. So this is what's left. That's your net ionic equation. All right, that's it for that one.